Now let's think about what happens to that transmitted light. So when a light wave meets a boundary between two materials, part of the wave might be reflected, as we've seen, where we have the angle of incidence equals the angle of reflection. But part of the wave may also be transmitted. What happens to this transmitted part of the light? The transmitted part may experience a change in speed, depending on what's called the refractive index N of the two materials. Refractive index is the ratio of the relative speeds. So it's a unitless value. So unless N, the refractive index, is the same for both materials, the transmitted wave will be refracted in some way, and the light will appear to bend. If we look here, the transmitted path, if it wasn't refracted, would have gone straight ahead, but the actual path of the light here is indicated here in pink. So why does this happen? So if we look at this diagram here of wave fronts hitting an interface, we can think of this as N1 being air and N2 being water. As the wave fronts hit the interface, something happens, and there's a change in the wavelength. So the velocity changes from the air to the water, and this results in a change in the wavelength. If the velocity changes, then lambda must change because of the relationship velocity equals frequency times lambda. The frequency does not change. It can't. The wavefronts are coming at a particular timing, and this is not going to be changed by the fact that the waves are now entering into a different medium. So the frequency doesn't change, instead the wavelength changes as the wavefronts enter the new medium and bunch up around here. This is written as Snell's law, where the refractive index N1 sine theta 1 equals N2 sine theta 2. If N1 is larger than N2, the light bends away from the perpendicular, and if N2 is larger than N1, and this is what we've shown in this picture here, then the light bends towards the perpendicular. I remember this by remembering the acronym FAST, fast. If the wave is going faster, it moves away, and slower towards. You can always, of course, just draw the diagram and work it out from first principles too. Now you understand what's happening. There's an interesting application of Snell's law called total internal reflection. The question is, what happens when theta gets large? We have a critical angle, the critical angle theta 1, for which the refracted light ray just grazes the surface, i.e. theta equals 90 degrees. This is where the light is just escaping, just skimming the very surface, and you can see that in this picture here. Total internal reflection occurs at angles pictured here, theta 1, that are greater than theta critical. Total internal reflection occurs, and the light rays are not able to escape the surface into the different boundary. We've exploited total internal reflection to build optical fibres and instruments that are useful in terms of imaging inside the human body, the endoscope. So total internal reflection enables us to manipulate light via optical fibres. So these are fibres where the medium means that the light is no longer able to escape and be transmitted into the outside. So bunches of these fibres can be used to help us see around corners and bend light, and also inside the human body using an imaging device called an endoscope.